Okay, and my name's Gabriel. I'm going to be leading this workshop, and we've got two moderators as well. We've got Claire and Parth. Okay, so hopefully at the end we're going to do a general Q&A session if we've got time, maybe just a couple of minutes. Before that, we're going to do two-step questions. One of them you've been sent and hopefully have had a bit of a look at, and one of them you mightn't have seen yet. I just need to share my screen because I'm going to be videoing this. Okay, apologies for a bit. Okay, so can everyone see this okay? Grand. And if it's too small, can maybe one of the moderators put in the chat or something that it's not readable? I'll try and zoom in, but it's fine. Okay, grand. So this is the first step question we're going to look at, and it's the one that you have that you've been sent and hopefully have had a bit of a look at. Okay, so I'm just going to dive straight in. This is what we call the stem of the question. If you've done some step questions before, you will have seen that they have a certain structure to them sometimes, and quite often at the start there's this thing called the stem. That's either just a bit of information or maybe a part question that will be useful for the rest of the question. Okay, so in this case, the stem introduces this notation, which we're going to call the floor function. Okay, so it's when we read floor of x denotes the greatest integer less than or equal to x, and then we've got some examples here. So with an integer, floor of that integer is just going to be that integer because it is the greatest integer less than or equal to itself. For a positive number like 4.7, it's going to be 4, and for a negative number, say minus 1.5, it's going to be minus 2. Okay, and then we define this function f to be the floor of the chart's still right. It looks so it's going to be the floor of x divided by x. Okay, and note that it's not defined for x equals 0 because we're dividing by x, so it doesn't really make much sense there. Even though you might feel a bit funny about that because floor of 0 is 0, we still can't define this function here. Okay, so first here's a graph, and this is just y equals floor of x. And I'm just going to talk briefly about the endpoints of the intervals here. Okay, so at this point, at x equals 1, floor of 1 is 1. Okay, so floor of x at 1 is here. Okay, it's not here. This is an important point that we're going to be needing throughout this question. So any step just to the left of 1, the floor of that is going to be 0, like no matter how small, but at 1 it's actually 1, so it's not 0. Okay, fine. Right, so this is the very first part of the question, and it's just asking us to sketch the graph in a certain range. Okay, so hopefully you can see this okay. I'm going to use darker pencil. Okay, x and y. Okay, so first let's just think about maybe the simplest interval to think about, which is 0 to 1. Okay, so we're not going to be taking the point at 0 because it's not defined there, but for all the points in between 0 and 1, the floor of that number is just going to be 0. So it's going to be 0 over some number, so our graph is 0 here. Okay, Now, at 1, it takes value 1, as it does at all the integers. Okay. No, this is a bit, can you definitely see this okay? And so let's look at this bit just between 1 and 2. So for 1 less than or equal to x less than 2. So for all the numbers 1 less than or equal to x less than 2, the floor of that number is 1. So here, in this unit interval, the graph is just going to look like 1 over x. Okay, I'm just going to attempt to draw that. I don't claim to be an artist, but give it a go. Okay, now note here, it's going to be almost 1/2. Okay, and it never actually gets to 1/2, but it gets kind of as close as you like as we get very, very close to 2. But just note that it won't actually be 1/2. Then again here, for 2 less than or equal to x less than 3, the floor is going to be 2, so we've got 2 over x, looks like that. And on this side, this between -1 and 0 is going to look like -1 over x. So it's going to asymptote to the y-axis. Between -2 and -1, it's going to look the same as -2 over x. So kind of going to something like this, and that's at 2. But again, it's not actually going to have that value. Okay, and similarly, it's going to do something similar. Okay, so I have a prettier one that the computer did earlier. Maybe you can't see it completely, but it's largely the same thing. And this is all you'd be required to do from 3 to -3 for this part. Okay, yeah, there's some maybe handy notation here. We can use a hollow circle. I don't know how well you can see that, but add here to show that we're not actually taking that point. Okay, we can equivalently also use like a filled in circle to show that the function has this value at 2, so it's equal to 1. Okay, so that's maybe some good notation. You could draw this on. It's not necessarily necessary. Okay, so that is the first part. So this is the next part of the question. By considering the line y equals 7/12 on your graph, or otherwise solve the equation f of x equals 7/12. So a good idea if they tell you to consider something is to consider it. So if we take our graph that I have lost, now let's think about this carefully. At this point here, it's 1/2. Okay, so it doesn't take this value, but that is where this hollow circle is centered on. Okay, and at this point, we've got another hollow circle, and that one's going to be 2/3 because this is in the section 2 over x. Okay, now 7/12 is exactly halfway between 1/2 and 2/3. So we can draw our line 7/12 like this. Okay, so we've drawn our line. They've told us to consider this line y equals 7/12, and we've drawn it. And now we can look for the solutions simply where our function f crosses this line. That's when we solve the equation f of x equals c. Okay, so we see there's not going to be any solutions on for negative x because it's always greater than 1 there, greater than or equal to 1. And these branches here are going to get shallower and shallower as we go more this way. So we see that there's only going to be this one solution on this branch. Okay, about here. Okay, so now we can set up an equation. In this bit, the graph looks like 1 over x, and we're just trying to find when 1 over x is equal to 7/12, and hopefully that means x is 12 over 7. Okay, fine. So that's the first bit of this first bit. Okay, so now we have to solve the equations. F of x is 17 over 24 and f of x is 4/3. So it was helpful to draw the line y equals 7/12 the first time. So let's do it again and see what happens. So this time 17 over 24 is ever so slightly greater than 2/3. We can write 2/3 as 16 over 24. And that's less than 17 over 24, which is less than 18 over 24, which is 3/4. So this time, this time we're going to hit both the first of two branches, but not the next one because it goes down to 3/4. Okay, let's draw this. And we can see our two solutions. And now we need to solve it for both of those ranges. So I'll kind of divide my page up here a little bit. So for f of x, we've got two possible solutions where 1 over x is 17 over 24, getting us x is 24 over 17. And also where 2 over x, because we've got this branch which looks like 2 over x. 2 over x to be 17 over 24, and we solve that to get x is 48 over 17. And these are our two solutions. Okay, finally we have to solve 4/3, same drill. Okay, it worked twice, why won't it work again? Now, first let's think, at this point here, okay, we're not taking this value. So that's a hollow circle. Okay, it's quite small, but it is. And in that branch, the one that's kind of just cut off here, the floor is -4. Okay. And so as we get very, very close to -3, this is going to get very close to 4/3. So we can kind of see that 4/3, okay, it doesn't look like 4/3, but it's fine. And it's going to go straight through that hollow circle. Now we've got 3 solutions, okay? Note it's not the 4th solution because it is going to the hollow circle and we're not taking the value there. Okay, and we can do, once again, the same thing. For f of x is 4/3. We've got 3 sections where -1 over x is 4/3. So x is -3/4. Where -2 over x is 4/3. So x is -3 over 2, and where -3 over x is 4/3, which gets us x is -9 over 4. Okay, and these are all our solutions, okay, because we can see all of these branches are going to get shallower, and it never hits, f of x is never greater than 1 on the positive x's. Okay, so here's just a possibly slightly prettier graph showing exactly what's going on here. And we've got the 1 solution, 2 solutions, and you need to give both. You need to give all the solutions that we can find. And yeah, that's a useful tip as well there. Okay, let's go to the last bit. This is definitely the hardest part of this question, these 2 parts. So first we have to find the largest root of the equation f of x is 9/10. Okay, so let's go back to our graph and find which one to use. Okay, so if we think about our line, that's going to be 9/10. It's going to be just below 1 here. So it's not going to have any negative solutions, and we're going to be looking for some positive solution that's out here somewhere. Okay, now the endpoints here that we weren't taking the value from were a half, 2/3, 3/4, 4/5. So on the interval 9 less than or equal to x less than 10, the floor of x, or sorry, f of x is going to be the floor of x, which is 9, over x. Okay, and as x gets very, very close to 10, this is going to get very close to 9/10. So we see that one of the branches is going to just not quite take the value 9/10. Okay, so somewhere along here we've got a branch that looks like this. It's got a hollow circle, and this is at a height of 9/10. So that means the greatest solution is going to be in the branch that was just previous to this, okay, which is going to be 8 less than x less than 9. So that means f of x is going to be 8 over x, and we're asked to solve this equal to 9/10 to get us x is 80 over 9. And that is our greatest solution, okay? It would be helpful to write, we can't have any greater because for all x greater than or equal to 9, f of x is always greater than 9/10. Okay, just say something that we can't solve this. This must be our greatest solution. Okay, and then the last part is give necessary and sufficient conditions in the form of inequalities for the equation f of x equals c to have exactly n roots. Okay, so first let's talk about that phrase necessary and sufficient conditions. Okay, because this is a thing that will pop up quite a bit in STEP, and you need to be comfortable with what you're actually being asked to do. So if I've got a statement, a necessary condition for that statement is one that must be true in order for my statement to be true. Okay, so this is useful because if my necessary condition is not true, then my statement is definitely false. A sufficient condition is slightly different. A sufficient condition is one for which it is enough for that to be true in order for my statement to be true. So if someone can tell me, yes, this sufficient condition is true, then I know my statement is true. Okay, and a helpful way to think about this is in terms of implications. So if I write P, where's my pencil? If I write P implies Q, where P and Q are just statements, then that means if P is true, then Q is true. Similarly, if I write P and the arrow going the other way, that's just exactly the same as saying Q implies P. Okay, or you can say that P is implied by Q. So we can kind of combine these into P implies Q and P is implied by Q at the same sense. So now we say there P if and only if Q. Okay, so this is this is saying that P and Q are equivalent statements. Okay, so in order to find necessary and sufficient conditions, it's helpful to look for an if and only if equivalence between number of roots and something else that's easy to work with. So in this case, as has kind of been pushing us towards throughout the whole question, we can kind of find our roots by drawing a straight line, or for f of x equals c, we can draw a straight line y equals c and see where it hits our graph f of x. So we can write down the equivalence. F of x equals c has exactly n roots if and only if. By the way, if and only if you also sometimes see written as IFF. And so f of x equals c has exactly n roots if and only if the line y equals c crosses y equals f of x exactly n times. Okay, so let's go back to our graph again. Maybe not this one. Got too many of these ones. Okay, so first of all, we can kind of eliminate some regions of C. if C is less than 0, then we definitely have no solution because f never lives down there. If C equals 0, then we're going to get infinitely many solutions because f is this entire interval, not taking the endpoints. So that's not helpful either because we're looking for n roots, exactly n roots, where n is an integer greater than 1 and infinity is not that. And also f never lives between 0 and a half. Okay, so we've got no solution there. So let's split this into, oh, and c equals 1 isn't helpful either because we've also got infinitely many solutions at all the integers except 0. So let's look at what we need for one solution on the right-hand side. Perhaps if I, okay, maybe that's not helpful. To get one root, okay, when, so I'm going to do this. Sorry, this is slightly confusing, but it's just so I've got the graph and what I want to write on the same page. So let's look at c less than 1. Okay, we don't have to worry about the left-hand side of the graph here because it's always greater or equal than 1. So here, to get one solution, we just need any line that only goes through the first branch, but none of the others. Okay, so it can be anything from y equals a half, but not taking that value because the branch doesn't actually attain the value a half as we've written with this cycle, up to 2/3. Okay, so for one root, we want half less than x less than 2/3. But this inequality here is strict and this one is not. Okay, because for example, if x was equal to a half, then we'd only have we'd have no solutions because the branch doesn't actually reach the half. Okay, so I'm sure you can see what's about to happen. If we go 2 roots, again, we need to go through the first 2 branches, but none of the others. So we get this. And in general, n roots, we've got n over n plus 1, 2, 2, less x less than or equal to n plus 1 over n plus 2. Now it'd be nice to write some justification of this rather than just spotting a pattern and writing it down. And just say, you know, if x was less than or equal to n over n plus 1, then we would hit fewer than n branches. And if it was greater than n plus 1 over n plus 2, then we'd also hit like some of the next branches along. Okay, fine, so that's for c less than 1. What about c greater than 1? Well, it's a similar sort of scenario. Okay, we're moving our line down like this, and we're going to hit 1 root, then 2, then 3, then 4, then 5, then 6, and 7. So if we're looking to get 2 roots, for example, remember we're not taking this value, so we need x to be, oh, sorry, stupid. We need c to be less than 2. Okay, we can't have it equal to 2 because then we've only got 1 root. And here the value is 3 over 2. So it's got to be less than or equal to 3 over 2. Okay. And again, you can spot our pattern. If we're going to keep going, we need to always hit the first n branches going left, but not the n plus 1th. So we want this to happen. Okay, so it might be tempting to say, oh, we're done. But you just need to be quite careful because this doesn't work for n equals 1. Because then 1 minus 1 is 0, and we're divided by 0, and we've tied ourselves in knots. So this is only true for n greater or equal than 2. And then you just need to say what happens when c is greater than 1 and n equals 1. You need just to hit this big long asymptotic branch, but not actually get to 2. Or not get to the second branch rather. So then we need c greater than or equal to 2. Okay, so these are our conditions for c less than greater than 1. And this. Okay, so these are what you'd need to give. And note that we've got different cases. So we've got split it by c's and then also by the n's in this case, because we've got this dodgy bit. And then you would also want to say c is not going to be less than or equal to a half, is not going to be less than 0 or equals 0 or 1. Okay, fine. So that is the first question.
Can I just jump in for a second?
Yeah.
Because I'm not sure that everybody realises we have a chat function on Zoom. So if you want to ask any questions at any point, we might not respond to them immediately, but you can post them in the chat. So it's down at the bottom near where participants is, a little speech bubble. So do feel free to write something in the chat if you want to ask something or anything at all. Okay, but I'll hand back over.
So just get our next question ready. Okay, so the next question is okay, so it's the step question from 2005. Okay, maybe it's not focused. Step 1, question 1. And this is available on the STEP support program. This is assignment 6, I think. I don't know if you've seen that online. I'm sure you'll be told about it at some point during today. It's a really amazing resource, and it got me through STEP anyway. So this is one of the questions. And I've introduced it simply because it's a good example of doing a STEP question carefully, but also there's an interesting formula that we can talk about. Okay, so the first bit is, I guess you could call this the stem, but it's very simple. Just this is what we mean when we say adding digits up, and it's exactly what you'd expect. Okay, so the first part is show that there are 15 5-digit numbers whose digits sum to 43. Okay, and you have to explain your reason carefully. So whenever they say show that, you need to be able to justify it with steps that are easily verifiable, and because they're giving you the answer, rather like so. Especially when they're saying show that there are 15. Okay, we have to show that there cannot be less than 15 and there cannot be more than 15 either. Okay, so that's an important point. Okay, so let's just think about this. Can you see? Okay, so the first thing I did whenever I was trying to solve this question was just thought about, we're trying to get 43. We've got 5 numbers. Okay, and these numbers are limited to 0 and 9. And I just kind of thought about the average 43 over 5. Okay, like as in the mean. So this is 8.6. So already we can kind of see we're going to need some quite big numbers, like quite big digits in here. We're not going to have lots of 2s and 1s and stuff floating about, because then we're not going to be able to get this average 8.6 out of 5 digits. Okay, so first let's start off just thinking about how many 9s we have, because 9 is the biggest digit. So if we had 5 9s, okay, that sums to 45, which is bigger than what we want, but it's quite close. Okay, so let's think how we can modify this in order to get 43. So we could lose one of the 9s and substitute it for something else. So 4 9s. Okay, we could substitute a 9 for a 7. Okay, I'm writing this kind of in shorthand so it doesn't take ages. And we want to think about how many ways we can, how many different numbers we can make out of this. Well, we've got 4 9s and 1 7. Okay, so that's a pretty simple way of thinking. We just got 5 slots. And I know one of these slots has to be filled with a 7 and the rest are 9s. I've got no choice over that. So I've clearly got 5 choices. So where to put the 7, and I've got 5 different 5-digit numbers. Okay, so we've got 5 possible choices here. What about if we've got 3 9s? Okay, so now these sum to 27. And we're trying to get to 43, which is 16 more than that. And we're trying to get 16 out of any digits 0 to 8. And we've only got 2 to play with. And we see the only way to do this is with 8 and 8. Okay, so we need 2 8s. So now we want to think about how many 5-digit numbers can we make with 3 9s and 2 8s. So there's 2 ways to think about this. Perhaps the way you might think of first whenever you're just trying to do this, kind of the natural way, is again just the 5 slots. I'm not saying this is necessarily the way you will think of it, but it's a relatively simple way of thinking about it. And now we've got 2 8s to put in here, and then all the other places are decided to be 9s. So if I put my first 8 in my first box, then I've got 4 choices for where I put the next 8. So I've got 4. If I put my first 8 in the second box, then I have 4 places to put the next 8, but I've already counted this version where we've got 2 at the start. So it's I've only got 3 choices to make 3 new 5-digit numbers. Similarly, if I put the 8 here, I've only got 2 new 5-digit numbers I can make. And then if I put it here, I've got no choice because I'll just make one that I've already made. So these sum to 10. Okay, so it would be very, very tempting to kind of stop here. It's like, whoa, I got to the magic number 15 and I'm done. But you need to show that you can't get more than 15 because otherwise you haven't shown that there are 15. Okay, so we've done all the cases, 5 9s, 4 9s, 3 9s. Now, if there were 2 9s, okay, these sum to 18, and we're trying to get to 43. So 43 minus 18 is 25. And we've only got the 3 digits from 0 to 8 to play with. And we see that the biggest we can make is 8 plus 8 plus 8, which is 24. So we're not actually going to be able to make it. So that is enough to show that we cannot make any more 5-digit numbers with their digits summing to 43, because 2 9s isn't going to work, and 1 9 isn't going to work, and 0 9s isn't going to work. You can write those down as well, but that's the good reason why. Okay, so that's how you show there are 15. Now, the reason I wanted to talk about this question is because you can kind of crush this question if you know a certain, formula. And this is called the multinomial coefficients. So you've probably heard of the binomial coefficients, or well, possibly. Okay, and we write them like that. And so that you would read that as n choose k, and that is the number of ways to choose k objects out of a lineup of n. Okay, and you can verify to yourself that is going to satisfy that formula, n factorial over k factorial times n minus k factorial. So now the question is, well, what about if I've got n objects? Okay, so say n balls, and I want to put them into M bins. Okay, and these bins have specified like sizes, the number of balls they can fit. So let's let the bins have sizes like B1, B2, up to BM, because there's M of them. That's not very clear. Okay, and we have N balls. Okay, now there are N factorial ways of messing about all the different balls. Okay, because say I had my N balls here and N slots for them here. I have N choices for which ball I put in here. But then I only have N minus 1 choices for which ball I put in here because I've already used up one. And then similarly N minus 2. And then down to the very end, in the last slot, I've got no choice because I've only got one ball left in one slot. So the number of permutations, so the number of ways of kind of messing about these balls, is N factorial, which is N by N minus 1 by down to 2 times 1. But now if I'm putting them into boxes or bins, then I don't, and I'm just asking for the number of ways to do this, I don't care how they're ordered in each bin. So say I'm putting them into bins, and say one of the bins has size 3. So as in there are 3 balls in here. Now, I've counted this 6 times because there are 3 factorial ways of permuting the balls in this bin. Okay, and 3 factorial is 6. So if I want to count, if I want to correct for this overcounting that I've done, I need to divide by 3 factorial. Okay, and I need to do this for all the bins. So that means the number of ways of putting these N balls into my N bins is going to be N factorial over B1 factorial times B2 factorial all the way up to Bm factorial. Okay, so that's, maybe it's best to put brackets around these. So, and B1, remember these are the size of the bins. And each term on the bottom here corrects for the overcounting I've done in each of those bins. Okay, and we write this as, like, the notation is B1 comma B2 Bm. So note that B1 plus B2 plus ... plus Bm has to be M. So this is something called the multinomial. Coefficients. And it'll tie into whenever the binomial coefficients are the coefficients of the expansion, say x plus y to the n, then multinomial are the coefficients of x plus y plus z plus ... plus w, where there's m in here, to the power of n. Okay, so you can read up with that. There's some pretty formulas to do with them and connections to the binomial and all the rest of it, and some interesting statistics and probability and everything. But for now, we can just think about this as a nice formula that we've got. If I've got n things and I want to split them into different groups of different sizes, I just plug the numbers in and I've got my formula. Okay. So now we come to, so in the previous part, when I had 3 9s and 2 8s, okay, and I was asking for the number of 5-digit numbers I could make out of this, I could have done 5 factorial over, oh, it's not focusing, is it? 5 factorial over 3 factorial 2 factorial, because I'm trying to split 5 objects into a group of 3 and a group of 2. And I'm asking how many ways are there to do this. Also note that 3 plus 2 is 5. Okay, and you can calculate this and find out that it is indeed 10, which is what we wanted. Okay, so now the second part is how many 5-digit numbers are there whose digits sum to 39? Okay, so this is quite similar to the first part. Oh, by the way, a helpful point in STEP is that if parts are labeled I, etc., then they're most likely linked. Okay, so perhaps what you did in part I will be useful in part II. Okay. If, however, they're labeled, say, A, B, C, the parts may be all related to some overarching stem, but they're not necessarily linked to each other. Okay. So we've got how many 5-digit numbers are there whose digits sum to 39? So it's slightly different because it's not telling us the answer this time, and we've got to come up with the answer. And whenever we've used a technique in the first part, the best thing to try usually is just fire ahead and try and use that same technique in the second part. And maybe it'll turn out to be algebraically horrific, or there's going to be way too many cases, or just it's going to give you nightmares. Then maybe you'll have to think of something cleverer to do and go back to the first part and see how that can help. But first thing to try is just fire ahead and try and use our same technique. Okay, so let's count the nines. So we're trying to get to 39. So again, 5 nines isn't going to be much help, but it's quite close. So what if we change to 4 nines and one other number, and 4 nines sum to 36, so obviously the other number has to be 3. Okay, how many ways are there to do this? Again, we've got 5 places to put the 3, and all the rest of the positions are already chosen for us to be nines. So we've got 5 ways. Okay. Also, you could use the multinomial formula here, or multinomial coefficient, because 5 factorial over 4 factorial, 1 factorial is just 5. Okay, so what about 3 nines? Okay, so these sum to 27, and we're trying to get 12 out of the next 2 digits. Okay, so there are 3 ways to do this without any nines. 8 and 4, 7 and 5, or 6 and 6. Okay, so let's consider this case first. We've got 3 nines, an 8 and a 4. And we're asking how many 5-digit numbers can we make out of these digits here? And we can plug straight into our multinomial formula. Okay, so we've got 5 things. So on the top, it's 5 factorial. And then on the denominator, we've got a group of 3, so 3 factorial, group of 1, 1 factorial, and group of 1, 1 factorial. And you figure that out to be 20. Okay, you could also just count this kind of in the natural way and said, okay, I can put an 8, and then I can put all the 4s there, and then I can put the 8 here and put the 4 in the next 2 slots, and so on. And then I can kind of do it the other way, where I've chosen the 4 and where can I put the 8s. Okay, it is exactly double of our 10 when we have 2 8s. Okay, then the 7 and 5 case is going to be exactly the same, isn't it? It's going to be 5 factorial over 3 factorial, 1 factorial, oops, 1 factorial, mixing up my 1s and factorials. And again, that's 20. Okay, now the 6 case is slightly different. Okay, it's the same as our 99988 case that we had previously, because now before we had 98994, which is different to 94998. But if I had 96996, if I swap the 6s, obviously it doesn't change anything. So we're going to have half the number of 5-digit numbers we can make here. Again, you can put that into your formula, 5 factorial, 3 factorial, 2 factorial, and that gets us 10. Okay, fine. So that's all of the things that happen when we've got 3 nines. So now let's go to our case of 2 9s. So these sum to 18, right? So then to get to 39, we need to make 21 using only 8s or less. That's not focusing again. Okay, grand. So how could we do this? Well, if we just start using 8s, okay, so 3 8s is going to be too much, but let's use 2 8s. So we get an 8, an 8, and a 5 will get us 21. 1 8 with a 7 and a 6 will get us 21. Is there any other way to do it with 1 8? Not really, because if we add 7, then we have to add 6, okay, and we can't add anything else. And then if we've got no 8s, we can obviously do it with 3 7s. Let's just use our multinomial formula again and again. 5 factorial over 2 factorial from the 2 9s, 2 factorial from the 2 8s, and 1 factorial. And that's going to be the 2 is going to cancel, 2 is going to take out the 4, so it's going to be 5 by 3 by 2, so it's 30. Have I lied there? No, I haven't. Have I? No. Okay. And the, okay, so 30. This case, we've got 5 factorial over 2 factorial from the 2 9s, and all of these are different. It's 1, a 2, and a 3, or a 1, a 1, and a 1. A 1, oh dear, I'm struggling to write here. That gets us 60. And here we've got 2 9s and 3 7s, so it's going to be 2 factorial over 3 factorial, and that will get us 10 as before. Okay, so that was all the ways of doing it with 2 9s. Can we do it with 1 9? Let's see. So that obviously sums to 9, and we're trying to get 39, so we need 30 out of the other 4 digits. So let's try and use it. We've got 4 8s will make us 32, so we can still do this. So what about, let's try 3 8s. Notice we're using the same technique as we used for our 9s to kind of systematically list all the cases with 8s. So an 8, an 8, and 8 will get us 24, so then we'll need a 6. And then what if we had 2 8s? Then we're trying to get 14 out of the next 2. We're only allowed to use 7 or less, so the only way to do that is 7 and 7. Once again, our formula, 5 factorial over 1 factorial from the 9, 3 factorial from the 8s, and 1 factorial from the 6. And that gets us 20. And this one is 5 factorial, 1 factorial from the 9, 2 from the 8s, 2 from the 7s. Okay, and once again, that gets us 30. Okay, what about...
we're just about running out of time, I think. It's almost 4 o'clock.
Okay.
So if you can give them a quick 2 minutes, how to finish off the question, that'd be absolutely fab.
Yeah, no problem. So then, again, we'll do it with 0 9s. And then we can only use 8s to get to 39. Again, we can do this with 5 8s, or to get to 40. So then you would do exactly the same case by case with the 8s. Use your formula once again, and then add up all the numbers we've circled. Okay, so this is a nice, the last thing I want to say about this really is, it's a good way to lay out your question is, okay, I've used shorthand a bit because I've been talking while I'm doing it, but to do it really systematically, case by case, explain why you're doing it and make sure your answers are clear. And then I think the final answer is 210, if you want to try that.
Right, thank you very much, everybody. If you want to leave room now, and then possibly leave the meeting, I don't know, but if you just leave the breakout room, and then we'll see what's happening. Thank you, everybody.